Welcome friends. Today we shall deal with Newton-Raphson's method. And Newton-Raphson's method is the one which is used for finding roots of the equation. So that is an iterative method in which we can approach closer and closer to the roots. Nowadays things are very simple with computers use, and we can rapidly see the graphical outputs using the new computers we have. We can visualize things, we can simulate things, and we can animate things. Now the present work, this present lecture deals with how Newton-Raphson's method work. I shall explain you in a graphical sense as well with equations, and then we shall apply this to one equation. Now let us suppose that we have some polynomial y equal to f of x. It can be in general expressed by summation ai x to the power I, where I rolls from 1 to m. Here m is the degree of the polynomial. So anything can be encompassed into this general equation. And now to find roots, it means that one needs to equate this equation with 0. That is, when y value is 0, that we call root. That particular value of x for which y is equal to 0, that is root. For quadratic equations, we have simple situation. We have two roots, and if it is cubic equation, it may have three roots, and so on. Now, I shall begin with a very simple example that we have a polynomial y equal to x square minus 13x plus 36. Obviously, you can make out that the factors are x minus 4, x minus 9. That is, we have roots 4 and 9. We are beginning our discussion with this pre-hand knowledge. Now in polynomial expression, we have a1. In this equation, the coefficient of x square is 1. Then coefficient of x is minus 13, and coefficient of x to the power 0 is 36. So we have a2 is equal to 1, a1 is equal to minus 13, and a0 is equal to 36. Now we can plot this equation very easily using any software kind of Microsoft Excel or anything like that. I have done this plot in Excel, and you can clearly see that the points are the points plotted, and the line joining them is a continuous line, and it intersects x-axis at x equal to 4 and x equal to 9. Now friends, these are the two roots of the polynomial that we are considering, which is basically y equal to f of x and y is equal to 0, and those values, I mean x value in x axis intersects the polynomial at 2 points, and those are the roots. Now I shall explain you graphically how things move. Now in this method, we have to start with an arbitrary starting point. That is the very drawback of the system. Now let us suppose that we have arbitrarily selected one point P x0 y0, and this point is a starting point which is to be considered in an arbitrary way. And here x0 is the x coordinate and corresponding y coordinate is y0. Now if you differentiate this equation y equal to f of x and find its value at x0 y0, then it will describe a line which is tangent to the curve at x0 y0. Now we are interested in finding the equation of this line, and obviously one point on the line is x0 y0, and we have a new point here x1 on x-axis, and obviously corresponding y is 0. So we have a line passing through 2 points, and we can find out slope for the line and the constant, that is y-intercept. For this particular point where we have x1, we have corresponding y1 that you can calculate using this polynomial equation. So we have started with an arbitrary point x0. For that we have calculated y0 using this polynomial. Then we have tried to find the equation of the line which is tangent to the curve at point x0, y0. We have intercepted with a point x1, and uh, corresponding to that we have found the point y1 from the polynomial. So in a sense we have jumped from x0 y0 to x1 y1, so that we are closer to the root of the equation. Now in the second attempt what we shall do, we shall find tangent at x1 y1. So tangent at x1 y1 will intercept somewhere here close to the root, and corresponding to that we shall be finding here x2 y2, and in the iterative attempts we can go closer and closer and closer to the root in the number of attempts. Now I'll explain you how mathematics works behind. Let us suppose that y dash is dy by dx, that is derivative with respect to x, and that we shall write f dash x. Now our basic equation was x square minus 13x plus 36. Its derivative is 2x minus 13. Now 2x minus 13 is to be found at point x0, y0. So you can find out slope using that. That will be a numerical value, slope of the tangent, and that tangent equation in general can be expressed as y equal to mx plus c. Now friends, we are looking at equation of the line which passes through 2 points x0, y0 I explained you, and x1 0, which is tangent to the curve. Now the slope of line will be y dash at a known point x0, y0. So m is equal to y0 dash, which is obviously f dash at x0. So f dash at x0 we have found here, which is represented in equation number 4. Now similarly you can extend the very equation y equal to mx plus c to write c. C is equal to y minus mx. So at point x0, y0, C is y0 minus y0 dash x0. And for point x10, x10 is also a point on the line which satisfies all conditions for the line. And for this point, if you substitute y equal to 0, it will be 0 equal to y0 dash minus, 0 equal to y0 dash x1 plus c. So this equation can be rearranged for c. Uh, this equation can be rearranged for x1 because x1 is the new point which is closer to the one of the roots of the polynomial. So rewriting this equation for x1, we have x1 is equal to minus c upon y0 dash. Now c is known to us. It is y0 minus y0 dash x0. You can substitute value of c and just simplify the equation so that x1 is equal to x0 minus y0 upon y0 dash. Friends, this is a very important equation and we are almost done. And you can generalize the equation. And here I have used a substitution h, which is minus y0 upon y0 dash. And in that form, we can write the next consecutive point which is in the close proximity of the root in terms of earlier point, and you can go on making such attempts until you reach to the root. Here I have already worked out a table for you which shows that in the first step my arbitrary start point is 1. Its corresponding y, which is y equal to f of x, we can calculate using the equation x square minus 13x plus 36. That turns out to be 24. Its derivative we have already worked out, and substituting value of x into that, it is minus 11, and you can calculate h. So in the next attempt we are calculating the point x1. X1 is calculated using this formula, x0 minus y0 upon y0 dash. So using that we have calculated h as 2.18, and 1 plus 2.18 is 3.18, and we are progressing to calculate value of y from the basic polynomial function, its derivative at the given point, and numerical value of derivative, and h which is minus y upon y dash. So earlier number 3.18 plus h will give you next point, and in this way you can go on progressing until you reach to the root. So fifth iteration is the root x equal to 4, and for that y is obviously 0 and y dash is minus 5, so h becomes 0, so there is no permitted addition into this, and we are stuck up in the iteration process to the root. This is how it works. Now in most of the universities one has to write a program for Newton-Raphson's method. In Nagpur University we have to devise a program in C or C++. So in this program, what are the input parameters? Basically one has to first set out what is the order of equation you are going to have. Once you write a program, you can solve higher order equations, which is manually little uh, tedious to calculate. Now, friends, depending on m, you have uh, coefficients a0, a1, a2, and so on up to an. If the equation is second order, we go up to a2. If it is cubic, we go up to a3, and so on. Then user has to specify the starting point, which is an arbitrary issue, and that is one of the drawbacks people talk in term as that the starting point is arbitrary. So you have to be a little selective by some some arbitrary technique, that which point should be closer to the root, and you have to start your iteration process from that point. Then the program which I have written, I have asked the user to specify how many steps he wants to perform uh, on iteration of the equation, and the value of n is to be inputted for that. Now the equation which we are using in the programming is x n plus 1, the next point, in reference to the arbitrary selected or known earlier point xn, minus yn upon yn dash. So y can be calculated by the polynomial, and y dash can be calculated from the first order derivative of the polynomial. So here the generalized equation yj I am writing as summation ai x to the power I, jth term. Its first order derivative function raised to n, we write n into function to the power n minus 1. So y dash will be I times ai x to the power I minus 1 for the jth term. Uh, we can find out roots of the polynomial if they are real, and if they are complex, we cannot work out that. When you write C programming for this kind of issue, then the things become very interesting, and I recommend students to write the program. I shall definitely narrate you the flowchart. Friends, I want to show you the flowchart that can be used for programming. So the oval shape entity indicates a start point. Here the first point is that we are getting scanf the degree of polynomial. Whether you want a quadratic equation, you should write m equal to 2. You should key in the degree of equation. Then the moment we key in the degree of equation, for example cubic equation m equal to 3, then it will accept a3, a2, a1 and a0 coefficients. So we are into a loop where I rolls from 0 to m. So once this data is taken in, the next point asked is the starting point x0, and immediately how many steps you want to iterate. So here you can be rampant in giving little larger number of steps to work out, so that it covers your equation. Otherwise you have to key in your coefficients again and again. Here after that we are doing calculation of y for that particular point. For example, y1 is calculated for arbitrary x1. Then the next point is finding its derivative and working out the same. After that, you have to find the next probable point which is close to the root, that is our first iteration. So that is xn plus h, where h is equal to, I have already explained you how this minus yn upon yn dash appears. After that we want to see the output, and if the number of iterations are not completed, one has to repeat that, and at the output one has to see how the iteration is going up, and once the number of iterations to be worked is completed, the program stops. Now I want to show up certain things in Maple, in the sense that let us suppose that we key in our equation y of x is equal to x square minus 13x plus 36. Then we differentiate this equation with respect to x once. So that gives us 2x minus 13. We have already dealt with this. Now this equation is to be solved for its equality with 0, so that you can find the roots. And sorry, I messed up. First order derivative equal to 0 gives you the condition whether it has maxima or minima. So 13 by 2, that is 6.5, is the point where it can have minima or maxima. Let us check out whether it is minima or maxima. Second order derivative, right hand side of equation 1 is differentiated with respect to x twice. So that gives derivative of 2x will be 2 and minus 13 will be 0. So as this value is positive, the function has minimum. Now we can use a very simple command, plot right hand side of equation 1 in the range 3 to 10. Now I already know the range 3 to 10, because once it is intersecting with x-axis at 4 and then at 9, so I have selected the proper range, and here you can see the graph. This graphical output shows that the first intercept occurs at x equal to 4, and it has minima at 6.5, that is 13 by 2, and then again it hits your x-axis at 9. Now friends, if we start with a arbitrary starting point 0, it will go on iterating closer, 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 closer and closer to the roots, and at this the iteration will stop. Whereas if you start with x equal to 5 arbitrary starting point, then it will return in this fashion to the root 4. Similarly, if you start the iteration with x equal to 10, it will uh, go on iterating so that it reaches to the root x equal to 9. And if you start with some point x equal to 8, it will do iteration this way. Now, if you start your iteration with an arbitrary point 6.5, which is minima of the function, and first order derivative at the minima is 0, so your iteration formula will immediately stop working, because in that formula you have h is equal to minus y upon y dash, and for minima or maxima the derivative is 0, and in the denominator the moment 0 comes, the things are undefined. So this is one of the limitation you can cite regarding this. So you can, if the function has only root after passing through minima or maxima, then your iteration process will not cross minima or maxima. So you have to manually avoid that kind of situation. So you can look at this as one of the drawbacks of Newton's Raphson's method. Now I want to give you glimpses of how things work for C language programming. I have written a program. We shall run the program, and we shall key in this A0, A1, A2, and let us see what happens. Now friends, I have loaded nr-8a exe file that I have prepared you in CPP, C++, and the first dialog box appears on the screen as welcome for using numerical method of Newton and Raphson. Now here we are supposed to key in the degree of the polynomial, and the degree of the polynomial equation that we have considered for our discussion is 2. Then the next question asked is coefficients. The coefficient A0 is 36. Then A1 is minus 13. Then A2 is 1. So that was our quadratic equation. Now we have to begin the search. Let us suppose that we begin our search first from 0, and let us try to iterate some good number of steps. Let's say 6 steps we want to work out. So the moment we press enter, the iteration will take place, and here we get some output. So here you can see for n equal to 0, we have started with 0, that is x0 step was starting point 0. The respective y calculation from the polynomial was 36, y dash is minus 13, and h, which is y upon y dash, is 2.76. Next time it will add it, and this appears as x1 and so on. So we go on making calculation. So y is approaching to 0 in steps. Like for x equal to 0 it was 36. Then we are increasing x step by the iteration procedure that we have discussed, and y goes on reducing to 7.6, 1.05, 0.03, and so on and so on. So here for the 5th iteration we are jumping from 3.999988 to 4 because of this h, and here y is again 0, and this gives us the root of the equation, and obviously we have reached to x equal to 4. Now friends, we shall try once again the same story. The degree of the equation we are using is 2. A0 is 1, sorry, A0 is 36, A1 is minus 13, and A2 is 1. And here the starting point, now instead of 0, we have starting point say 3, and how many steps we want. In 5 steps we can get up to our answer. So for x equal to 3, it is obvious on the screen that x equal to 3 makes polynomial y equal to 6, y dash equal to minus 7, and h is equal to y upon y dash, so with a minus sign, that makes it 0.85. Then this is added to x0, that is our basic formula. So x1 is equal to x0 plus h, and we are calculating y for corresponding things, and every time we are adding h into it. That gives, in the third step, it gives 3.99999, that is 5 times 9 is 7, and h calculated is this. So you can see in the fourth step we reach to the answer which we desired. Now friends, we shall again repeat our problem. The degree is 2, A0 is 36, A1 is minus 13, A2 is 1, and this time our starting point is 5. Arbitrarily we start from x equal to 5, and the number of iteration steps, again I shall prefer 5, and see for x equal to 5, y is minus 4, y dash is minus 3, h is equal to minus 1.33. So the next point, it calculates, it takes it from 5 to 4. Earlier it was taking it from 1 to 4. So this is how it goes to the nearer root. Now we shall try some point near to the another root, which is 4. Again the degree of equation is 2. A0 is 36, A1 is minus 13, and A2 is 1. Now we shall opt x equal to 7, which is near to x equal to 9, and in again 5-6 steps we can get the root, and here you can see we are heading to the root 9. Now let us key in the starting point as 12, which is higher than x equal to 9. Our equation, sorry, we have entered degree 12. That's a mistake. So friends, degree is equal to 2. A0 is 36. A1 is minus 13. A2 is 1. And the arbitrary starting point is 12. And let us iterate some 6 number of steps. And here you can see that we roll from 12 to 9.8, 9.1, and finally you reach to the perfect number. Sorry. Now friends, I want to show you the most interesting part here that we encounter. A0 we have 36, A1 is minus 30 and A2 as 1. Now here we want to start at 6.5. This is a point where the function has minima, and at minima its first derivative is 0, and in the denominator h is equal to minus f upon f dash, so f dash will be 0. So here I want to enter some number of steps, say 5, and this will be stuck at floating point error, divide by 0, because f dash has gone into the denominator, which is 0, and that makes things not possible. So this is one of the drawbacks. Thank you. I wish readers to take a closer look at the table, and if possible to note down this table on a piece of paper, where we start our arbitrary iteration process at x equal to 1 and y equal to f of x will be 24 for x equal to 1. The slope of the tangent line is minus 11, which is y dash, and h is the x plus h, which is equal to minus y upon y dash, is 2.1818, and c equal to y minus mx, which comes originally from y equal to mx plus c line, and that is 35, and so on. In the different iteration process we are going through these numbers. And here in the fourth step itself, for x equal to 4, y is almost 0. 4 into 10 power minus 6, that's almost 0, but not 0 exactly. And in the next step, fifth step, it is perfectly 0. Now let us graphically go through the homemade animation through PowerPoint presentation. Now this is the graph of y equal to f of x, and here the graph begins at x equal to 3. The range of x-axis is x equal to 3 to x equal to 10. Later on in the next steps I am going to little change uh, the range of x so that we can zoom the thing that we are looking for. Now in this step we are starting from 0 to 10. And here on y-axis this is 20, the first iteration, arbitrary iteration, x equal to 1, y equal to 24, y dash minus 11, and y-intercept is 35. Here you can look at this blue line, which makes tangent at x equal to 1, intercepts y-axis at 35, and it hits x-axis at this point. The tangent point is here, then it hits x-axis at this point, which is 3.18 we have calculated in the table, and for that 3.18 arbitrary we can calculate y, and y is this value, which is 4.76. Now again we have to draw a tangent to the given curve at this point, and we shall proceed further. Now here again I have jumped on x-axis range. It goes from 1 to 4.5. 4 is the case where we complete our iteration. Now at 3.18 we have intersection with x-axis. The tangent is hitting x-axis. For that arbitrary value we have to find out y, which is 4.7, and y-intercept is 25.8. Now again x values are changing as I'm zooming into the graph, and here 3.18 is this point, corresponding is 4.7. For this we are drawing a tangent next iteration that is coming out. So at this iteration we are hitting x-axis at 3.899, that is almost 3.9. So 3.5, 3.6, 3.7, 3.8, 3.9. and this is the point where now we want to find derivative and then tangent and its x-intercept. So here the blue line indicates the tangent point and we are going closer to the root. So here I am showing you all tangents at the same time. This is the first tangent hitting x-axis. For this we are having value of y, then we are finding derivative there, then that tangent is hitting here, then corresponding y is this, then that tangent hits at 4, and that is we are done. So this is how we reach to the final iteration. I have graphically shown you how we progresses. I hope this clarifies to a quite better extent, and I recommend that you should try some another polynomial and try to find out the root. Thank you for being patient in listening. Thank you. For Maple students, I have got a very quick review to go through. Here we have entered the basic equation that we were considering for analysis, and then we had one derivative, and then again we have equated that first derivative with 0 so that we can find out maxima and minima, and the second order derivative is also found here, so that the sign of the derivative shows that it is positive and the function is minima. So you can basically plot this function. Equation number 1, right hand side we have picked up. This is our equation number 1, and along with that the first iteration line which is simultaneously plotted, that is indicated by this equation. And here there are some selections so that we can have title to the graph, size of the font, uh, type of the font, labels and all that, so that we can have look like this. Then in the second case, the range is changed, only this range is changed. Then in the third case we have again change of range. Then in the fourth case we have second line which is going closer to the root. Then we have third line from the table which is yet going closer to the root. And here we have had a plot of right hand side of equation 1, first line tangent line, second tangent line, third tangent line and fourth tangent line together. And here you can see the simultaneous plot, and here this violet line is almost passing through the point 4 on x-axis. So to just make a resolution clear, we have one more graph. So this is how you can work out things. You can have multiple plots, you can have multiple lines for the plot. So Maple student can exercise this problem also in the Maple laboratory, and I hope you will have a wonderful experience when you will work out that on Maple. Thank you.